Hello, in this lecture we'll answer two questions. In the first question, we'll find out the radius of this circle. And in the second question, we'll find out the area of this plane shape. So we'll start with the first question. In the drawing, we have quadrilateral ABCD that is described by this circle. Side AD of this quadrilateral ABCD equals to 6 units in itself, side AB equals to 4 units in itself, side BC equals to 4 units in itself, and side DC equals to 5 units in itself. And our task is to find out the radius of this circle. So first of all, we will define this angle BCB as alpha. Because of the fact that quadrilateral ABCD is exactly quadrilateral, the sum of those two opposite angles must be equal to 180 degrees. Here we have quadrilateral ABCD that is described by this blue circle, and therefore the sum of those two opposite angles must be equal to 180 degrees. That is to say, x plus y equals to 180 degrees. Likewise, the sum of those two opposite angles must be also equal to 180 degrees. That is to say, a plus b equals to 180 degrees. So, the sum of those two opposite angles must be equal to 180 degrees. So, alpha plus the missing angle, the total must be equal to 180 degrees. Therefore, the missing angle must be equal to 180 degrees minus alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of those two opposite angles, because quadrilateral ABCD is exactly quadrilateral. Therefore, this missing angle must be equal to 180 degrees minus alpha. In the next step, we will join points B and D together by a straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is triangle ABD, and the second part is the lower triangle PDC. So in the next step, we will implement the law of cosines on both those two triangles. We will implement the law of cosines in this green triangle ABD. Then we will implement the law of cosines in this lower triangle BCD. So, I repeat quickly on the law of cosines. The law of cosines is true in any triangle, so this is triangle ABC that could be any triangle. This is angle BAC that is equal to theta degrees in size. Side AB of this triangle ABC equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length. So, this triangle ABC that could be any triangle according to the law of cosines, the following equation is true. C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. So in the first step, we will implement the law of cosines. This great triangle ABD. So, according to the law of cosines, in this great triangle ABD, the following equation is true. BD square equals to AD square plus AB square minus 2 times AB times A minus 2 times AD times AB times cosine 180 degrees minus alpha. So it is all according to the law of cosines. This great triangle ABD, the following equation is true. BD square equals to AD square plus AB square minus 2 times AD times AB times cosine 180 degrees minus alpha. And again, according to the law of cosines, this can triangle ABD. The following equation is true. BD squared equals to AD squared plus AB squared. And again, BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. We have the trigonometric identity that says that cosine 180 degrees minus alpha equals to minus cosine alpha. Therefore, instead of cosine 180 degrees minus alpha in this equation by minus cosine alpha. So in total, we found out that according to equation 1, BD squared equals to AD squared. AD is 6, therefore AD squared is 6 squared, that is 36. Plus AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. Minus 2 times AB is 6 times, again AD is 6 times AB is 3 times, and cosine 180 degrees minus alpha is minus cosine alpha. So this expression we have minus times minus is plus. So this is a positive expression. So in total we found out that according to equation 1, BD squared equals to 36 plus 9, that is 45. And here we have plus, it is a positive expression, 2 times 6 is 12, and 12 times 3, here we have 2 times 6, minus 2 times 6 is 12, and 12 times 3 is 36, so it is 36 times cosine alpha. So in total, according to equation 1, we found out that BD squared equals to 45 plus 36 times cosine alpha. In the next step, we will implement the law of cosines in this lower triangle, triangle BDC. So according to the law of cosines, in this red triangle, in this white triangle BDC, the following equation is to BD squared equals to DC squared plus BC squared minus 2 times DC times BC times cosine alpha. And again, according to the law of cosines, in this lower white triangle BDC, the following equation is 2. BD squared equals to DC squared plus BC squared minus 2 times DC times BC times cosine alpha. So BD squared equals to DC squared. DC is 5, therefore DC squared is 5 squared, that is 25, plus BC squared. BC is 4, therefore BC squared is 4 squared, that is 16, plus 2 times DC is 5, times BC is 4, times cosine alpha. So in total, if you found out that BD squared equals to 25 plus 16 plus 2 times 5 times 4 times cosine alpha. So BD squared equals to 25 plus 16 is 41. Here we have minus 2 times 5 is minus 10, and minus 10 times 4 is minus 40. So in total this expression equals to minus 40 times cosine alpha. So according to equation 2, we found out that BD squared equals to 41 minus 40 times cosine alpha. Well, according to equation 1, we already found out that BD squared equals to 45 plus 26 times cosine alpha. So we have two different equations for BD squared, equation 1 and equation 2. Therefore, we will get equation 3. That states that BD squared according to equation 1 must be equal to BD squared according to equation 2. Very simple equation. BD squared according to equation 1 equals to 45 plus 36 cosine alpha. And it must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to 41 plus 40 times cosine alpha. So here we will subtract 41 from this equation, equation 3. So here 41 will get cancelled. So in this side of the equation we left only with minus 40 times cosine alpha. Well, on the other side of the equation we have 45 minus 41 is 4, so it is 4 plus 36 times cosine alpha equals to minus 40 times cosine alpha. So here we will add to this equation 40 times cosine alpha. So 40 times cosine alpha minus 40 times cosine alpha is 0, so we have 0. While on the other side of the equation we have 36 cosine alpha plus 40 times cosine alpha is 76 cosine alpha plus 4 equals to 0. Here we subtract 4 from the equation, and we get that 76 times cosine alpha equals to minus 4. So here we will divide this equation by 76, and finally we get that cosine alpha equals to minus 4 over 76. So minus 4 over 76 equals to minus 0.0526. So in total we found out that cosine alpha equals to minus 0.0526. So it is known. In total we found out that cosine alpha equals to minus 0.0526. We would like to find the value of alpha itself. In order to find the value of angle alpha itself, we just have to operate the inverse function of cosine on the results, that is minus 0.0526. In this way, we get the value of alpha itself. So the inverse function of cosine. Look at the inverse function of cosine on the result, that is minus 0.0526. So the inverse function of cosine of minus 0.0526 equals to 93.017 degrees in size. So alpha equals to 93.017 degrees in size. So as we know in the drawing, this is angle alpha, this is equals to 93.017 degrees in size. So in the next step, we will implement the law of sines. This triangle BDC. Triangle BDC is described by this circle. Why? Because all the three vertices B, C, and B lie on the circle itself. And therefore, because of the fact that triangle BDC is described by this circle, we can implement the law of sines in its full version on this triangle BDC. So I put the law of sines. The law of sines is shown in a triangle, so this is a triangle ABC that could be a triangle. This is angle BAC, this is equal to capital A degrees in size. This is angle ABC, this is equal to capital B degrees in size. And finally, this is angle ACB, this is equal to capital C degrees in size. AB equals to C units in itself, side BC equals to A units in itself, side AC equals to B units in itself. And this triangle ABC is described by this circle. The radius of this circle is R. So now drawing according to the law of cosines in the solution, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And R is the radius of this circle that blocks triangle ABC. But again, according to the law of sines, A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R, and R is the radius of this circle. So we can implement the law of sines in our drawing. So we focus on this triangle BDC, this is described by this circle. So according to the law of sines, we get that BD over sinus alpha equals to 2R. Again, in this triangle BDC, according to the law of sines, the following equation is for BD over sinus alpha equals to 2R. And R is the radius of this circle, that is the radius that we are looking for in this question. So before that, we have to find out the value of BD itself. According to equation 2, we only found out that BD square equals to 41 plus 40 times cosine alpha. BD square according to equation 2 equals to 41 plus 40 times cosine alpha. So BD square equals to 41 plus 40 times cosine alpha. And we found out that angle alpha equals to 93.107 degrees in size. 93.017 degrees in size. 0.17 degrees. So total, we find out that BD square, according to equation 2, BD square equals to 41, and minus 40 times cosine 93.017 equals to 2.105. This expression equals to plus 2.105. So total we found out that BD square equals to 41 plus 2.105 equals to 43.105. So total we found out that BD square equals to 43.105. Here we'll take a look at all those equations. And finally get that BD equals to the square root of 44.105. So BD equals to 6.565 units in Israel. And again, I should find out that the length of side BD is equal to 6.565 units in Israel. Okay, note BD equals to 6.565 units in Israel. So total it's measured the low size in this triangle BDC, and found out actually that BD of sinus alpha equals to 2R. And R is the radius of the circle that we are looking for. So BD is 6.565 over sinus alpha over sinus 93.017 degrees equals to 2R. So 6.565 over sinus 93.10 equals to 6.5745 equals to 2R. Total we found out that 6.5745 equals to 2R. Here we divide this equation by 2 and find that R equals to 6.5745 over 2 is 3.287 units in Israel. And again, so that we found out that the radius of this circle, that is the radius that we are looking for, this question is equal to 3.287 units in Israel. So finish to answer the first question. The next step, I present to the second question and answer the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the domain, we have the big quadrilateral ABCD. We know that AP equals to PB, side AD of this quadrilateral ABCD equals to 9 units in itself, side AC equals to 8 units in itself, and finally side BC equals to 7 units in itself. Those three angles, they're all right angles. Again, our task is to find out the area of this green shape. So first of all, we know that AB is a straight line. So if you focus on the lower side of the straight line AB at point P, here the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus this missing angle, total must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. According to Olympiad, it said that the sum of the angles on one side of the straight line is equal to 180 degrees. This missing angle must be equal to 90 degrees in its size. In the next step, we join points A and Q together by straight line. Likewise, we join points B and Q together by straight line. In the next step, we prove that the white triangle APQ can go into the green right triangle PQB according to side angle side rule. So we have to prove that this is the white triangle APQ. That this white triangle APQ can go into this green triangle PBQ. So, what those two triangles can run into each other. First of all, AP equals to PB according to what is given as a question. And again, side AP of the right triangle equals to side PB of the right triangle according to what is given as a question. In addition, those two angles are both right angles and therefore they are equal to each other. So actually, this is angle APQ. Of the right triangle APQ, it is equal to this angle. This is actually angle BPQ of the green triangle BPQ. And again, so that we should find out that angle APQ of the white triangle equals to angle BPQ of the green triangle. They're both equal to 90 degrees and therefore they're equal to each other. Finally, side PQ is a common side that belongs to both triangles, so we can find out that PQ equals to itself is a common side that belongs to both triangles. PQ equals to itself is a common side that belongs to both triangles. So in total we found out that the right triangle APQ can go to this green triangle PQB according to side angle side rule. The right triangle APQ can go to the green triangle PBQ according to side angle side rule. That is to say, we found out that those two sides, and the angle that is included between those two sides in this right angle corresponds equal to those two sides, and the angle that is included between those two sides in this rectangle. Therefore, those two rectangles can point to each other according to side angle side rule. Again, we have those two sides and the angle that is included between those two sides in this right angle corresponds equal to those two sides, and the angle that is included between those two sides in this rectangle. Therefore, those two rectangles can point to each other according to side angle side rule. And from the fact that those two rectangles can point to each other, we will derive two things. The first thing that we derive that they must have also the same area. Any two triangles that can point to each other, they must have also the same areas. Therefore, the area of this triangle APQ equals to the area of this triangle PBQ. Then again, the area of triangle APQ can point is equal to the area of triangle PBQ because they can point to each other. The second thing that we derive that AQ equals to QB. And again, we derive that AQ equals to QB. AQ equals to QB according to the rule that corresponding sides can point triangles are equal to each other. Those two triangles can point to each other, therefore their two corresponding sides must also equal to each other and their left. That is to say, AP equals to PQ. AP equals to QB. Here we square both sides of the equation. We get it AQ square equals to QB square. AQ square equals to QB square. AQ is the opponent of the right triangle ADQ. Again, AQ is the opponent of this right triangle ADQ. So here you can implement the Pythagoras theorem in this right triangle ADQ. According to the Pythagoras theorem, in any right triangle, the square of the opponents equals to the sum of the sides of the perpendiculars. So in this right triangle ADQ, it means that AQ square equals to AD square plus DC square. So AQ square equals to AD square plus BDQ square. Again, we just substitute AQ square by AD square plus DQ square. And it is equals to QB square. QB is the opponent of this again triangle BCQ, and therefore, according to the Pythagoras theorem, we get that BQ square equals to BC square plus CQ square. So we have QB square equals to BC square plus QC square. So in total, we found out that AD square plus DQ square equals to BC square plus QP square. So AD is 9, therefore D square is 9 squared, that is 81. plus dq square. We define the length of dq as x. dc totality is 8, therefore qc must be equal to 8 minus x. This dc is 8 minus x. So qc is totally equal to 8 minus x. So here we have 8d equals to 9, therefore d squared is 9 squared is 81. And we have in the question 2 also dq square. dq is x, therefore dq square is x squared. So it's total according to equation 2, 81 plus x squared equals to bc squared plus dc squared. bc is 7, therefore bc squared is 7 squared, that is 49. Plus qc squared. qc is 8 minus x, therefore qc squared is 8 minus x squared. So that, according to equation 2, if you found out that 81 plus x squared equals to 49 plus 8 minus x squared. So 81 plus x squared equals to 49 plus 8 minus x squared. 8 minus x squared according to the algebraic identity. Use the algebraic identity that says that a minus b squared equals to a squared plus b squared minus 2 times a times b. So according to the algebraic identity that I mentioned, 8 minus x squared equals to 8 squared, that is 64, plus x squared minus 2 times 8 times x, that is minus 16x. So here we have x squared on both sides of this equation, so x squared gets cancelled. So I cancelled x squared, and this side of the equation we have only if 81 equals to 49 plus 64 is 113. 113, and we have here minus 16x. So total, we actually found out that 81 equals to 113 minus 16x. Here we add 16x to this equation. So if 16x will get cancelled, so in this side of the equation we have only 113 equals to 81 plus 16x. Here that's 16x, so this equation is right. So that we should also that according to equation 2, 16x equals to 16x plus 81 equals to 113. Here we subtract 81 from this equation 2, and get that according to equation 2. '81 minus 81 is 0, so here we left only if 16x equals to 113 minus 81 is 32. So in total, according to equation 2, we should found out that 16x equals to 32. Here we divide this equation by 16, and finally get that x equals to 32 over 16 is 2, so x equals to 2 units in its length. So dq equals to x, and x equals to 2. Here we have qc equals to 8 minus x. 8 minus x is 8 minus 2, that is 6. So qc equals to 6 units in its length. this is the big quadrilateral ABCD. And the sum of those two one-sided interrogants is equal to 180 degrees, and therefore, according to Rule 20, those two one-sided interrogants must be located between parallel lines. That is to say, AD is parallel to BC. Okay. So a page quicker on Rule 20. According to Rule 20, if the sum of two interior one-sided one-sided angles is equal to 180 degrees, then they must be located between parallel lines. So in the moment you have line A, line B, line C cuts those two lines, and those two angles are defined as one-sided interrogants. So according to this rule 20, if the sum of those two angles is 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Likewise, those angles are defined as one-sided interrogants. So if the sum of those two one-sided interrogants is equal to 180 degrees, that is to say if gamma plus beta equals to 180 degrees, then they must be located between parallel lines. Then line A is parallel to line B. Okay, again, the sum of those two one-sided interrogants is equal to 180 degrees. Therefore, those two one-sided interrogants must be located between parallel lines. That is to say, AD is parallel to BC. So if AD is parallel to BC, it means that quadrilateral ABCD is a trapezoid. Why? Because it has one pair of parallel sides. Therefore, quadrilateral ABCD is a trapezoid. So it is known quadrilateral ABCD is a trapezoid. So in the next step, we will calculate the area of this trapezoid ABCD in two different methods. Then we create a equation fit that said that the area of trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. So first of all, what is the area of trapezoid? This is trapezoid ABCD. The area of this trapezoid ABCD equals to the sum of its two parallel bases. That is to say, it is A plus B times the height over 2. Repeat again, in total, the area of this trapezoid ABCD equals to the sum of its two parallel bases. That's actually A plus B times the height over 2. So we can implement the equation that gives us the area of trapezoid ABCD. So the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that's actually AD plus BC, times the height is DC, divided by 2. And again, the area of this trapezoid ABCD equals to the sum of its two parallel bases, is actually AD plus BC times the height DC over 2. AD equals to 9 plus BC. BC equals to 7 times the height DC. DC equals to 8 over 2. So if you know that the area of trapezoid ABCD according to the first method of calculation equals to 9 plus 7, that is 16. Here we have 8 over 2 is 4. So it is 16 times 4, that is 64. 64 square inch in size. So the area of trapezoid ABCD equals to 64 square inch in size. So write it down. So according to the first method of calculation, the area of trapezoid ABCD equals to 64 square inch in size. We have another way to calculate the area of this trapezoid ABCD. Actually, we know that the area of trapezoid ABCD must be equal to the sum of the areas of the 4 components that it consists of. The 4 components are as follows. This right triangle ADC, and this triangle APQ plus this right triangle PQO or PQB plus this right triangle BCQ. So according to the first method of calculation, the area of this trapezoid ABCD must be equal to the sum of the areas of the 4 components that it consists of. If you know that the area of this trapezoid ABCD equals to the area of this right triangle ADQ, that is the first component that what the other ABCD consists of. The area of this right triangle equals to the base, that is the base is 2 times the height is 9 over 2. So 9 times 2 over 2 is 9. So total, we should found out that the area of this right triangle ADQ equals to 9 square inches in size. We already found out that triangle APQ can go into triangle PQB, they must have also the same areas. So if you find the area of this triangle APQ SA, then the area of this triangle QP must be also equal to A because they have the same areas. This is the first, the fourth component that for the other ABCD consists of. This is actually the right BCQ. So the area of this right BCQ must be equal to the base QC, that is 6 times the height BC, that is 7 over 2. So in total, the area of this right BCQ must be equal to 6 times 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. So in total, if you found out the area of this fourth component of the trapezoid ABCD, the area of this PQC equals to 21 square inches in size. So in total, according to the second method of calculation, the area of this trapezoid ABCD must be equal to 9 plus A plus A plus 21. And again, the area of this big trapezoid ABCD equals to 9 plus A plus A plus 21. 9 plus 21 is 30, and a plus a is 2a. So in total, according to the second calculation, the area of trapezoid ABCD equals to 30 plus 2a squared in its size. According to equation 1, we have found out that the area of trapezoid ABCD equals to 64 squared in its size. We have the area of trapezoid ABCD in equation 1 and equation 2. Therefore, we get equation 3 that says that the area of trapezoid ABCD according to the first method of calculation must be equal to the area of trapezoid ABCD according to the second method of calculation. We only found out that the area of trapezoid ABCD according to the first method of calculation equals to 64 squared in size. It must be equal to the area of trapezoid ABCD according to the second method of calculation. We only found out that the area of trapezoid ABCD according to the second method of calculation equals to 30 plus 2a. Actually, according to the first method of calculation, the area of trapezoid ABCD equals to 64. It must be equal to the area of trapezoid ABCD according to the second method of calculation. So we have found out that the area of trapezoid ABCD according to the second method of calculation equals to 30 plus 2a. So now if we found out that 64 equals to 30 plus 2a, here we will subtract 30 from this equation. We get it according to equation 2, 64 plus 30 is 34 equals to 2a. Here we divide this equation by 2 and get that a equals to 34 over 2. 34 over 2 is 17. So the area of this letter APQ equals to a, and a equals to 17. Likewise, the area of this letter APQ is a, and a is also 17. And we would like to find out the area of this red shape. The red shape equals to, the area of the red shape equals to 8 and 17 plus 21. Get the area of the red shape, that is the area that we're looking for in this question, equals to the area of this right again BPQ, that is 17 plus 21. So the area of trapezoid ABCD in total equals to 17 plus 21, that is 38 squared in size. So again, in total we found out that the area of this green shape, that is the area that we're looking for in this question, equals to 38 squared in size. So we finished the answer on the second question. The next step, I will summarize the lecture. That is to say, we will repeat on the solution of the first question, and then we will repeat on the solution of this second question. In the first question, our task was to find out the radius of this circle. So in the drawing, we have quadrilateral ABCD that is described by this circle. Side AD of quadrilateral ABCD equals to 6 units in itself. Side DC equals to 5 units in itself. Side BC equals to 4 units in itself. And finally, side AB equals to 4 units in itself. Again, our task was to find out the radius of this circle. So first of all, we define this angle as alpha. Quadrilateral ABCD is of course a cyclic quadrilateral, therefore the sum of those triangles must be equal to 180 degrees according to all 20. So page question on all 20. It is not all 20, this is the wall. In this moment, we have quadrilateral ABCD that is described by this blue circle. And because of the fact that quadrilateral ABCD is a cyclic quadrilateral, the sum of those two opposite angles must be equal to 180 degrees. That is to say, A plus B equals to 180 degrees. Likewise, the sum of those two opposite angles must be also equal to 180 degrees. That is to say, x plus y equals to 180 degrees. So actually, quadrilateral ABCD is of course a cyclic quadrilateral, and therefore the sum of those two opposite angles must be equal to 180 degrees. But this angle equals to alpha according to our definition, therefore this angle must be equal to 180 degrees minus alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of those two opposite angles inside the cyclic quadrilateral ABCD. Therefore this angle must be equal to 180 degrees minus alpha in its size. So in the next step, we join points B and D together by the line. By joining points B and D, we divided this quadrilateral ABCD into two parts. The first part is the green triangle ABD, and the second part is the white triangle DBC. So the next step, we implemented the law of sines on both those two triangles. So let's click on the law of cosines on both those two triangles. So let's click on the law of cosines. This is triangle ABC that could be any triangle. This is again BAC equals to theta degrees in size. Side AB equals to A units in itself. Side AC equals to B units in itself. And side BC equals to C units in itself. So in this triangle ABC that could be any triangle according to the law of cosines, the following equation is to C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. So the first step, we implemented the law of cosines. This again triangle ABD. According to the law of cosines, this again triangle ABD, the following equation is to BD square equals to AB square plus AD square minus 2 times AB times AD times cosine 180 degrees minus alpha. Since again, according to the law of cosines, this green triangle ABD, the following equation is to BD square equals to DC square plus BC square minus 2 times DC times BC times cosine alpha. Usually, we're talking about triangle ABD. The triangle ABD, according to the law of cosines, DB square equals to AD square plus AB square minus 2 times AB times AD times cosine 180 degrees minus alpha. And we have the trigonometric identity that says that cosine 180 degrees minus alpha equals to minus cosine alpha, therefore we can implement minus cosine 180 degrees minus alpha by minus cosine alpha. So in total we get that BD square equals to AD square. AD is 6, therefore AD square is 6 squared, that is 36, plus AB square. AB is 3, therefore AB square is 3 squared, that is 9. So we found out that BD square equals to 36 plus 36 plus 45, and cosine under integral minus alpha equals to minus cosine alpha. So this expression in total is a positive expression because minus times minus is plus. So in total we found out that BD square equals to 36 plus 9, that is 45, minus 2 times 6 times 3 times cosine alpha. So minus 2 times 6 is minus 12, and minus 12 times 3 is minus 30. This is a positive expression because minus times minus is plus, so it is plus 36 times cosine alpha. So in total, according to question 1, we found out that BD square equals to 45 plus 36 cosine alpha. The next step is when the law of cosines in this lower triangle BDC. According to the law of cosines in this lower triangle BDC, the following equation is to BD square equals to BC square plus DC square minus 2 times BC times DC times cosine alpha. And again, this lower triangle BDC, the following equation is to, according to the law of cosines, BD square equals to DC square plus BD square minus 2 times BD times DC times cosine alpha. So BD square equals to DC square. DC is 5, therefore DC square is 5 squared is 25, plus BC square. BC is 4, therefore BC square is 4 squared is 16, plus 2 times DC, that is 5, times BC, that is 4, times cosine alpha. So in total, we found out that BD square equals to 25 plus 16, plus 2 times 5 times 4 times cosine alpha. So BD square equals to 25 plus 16 is 41, plus 2 times 5 times 4, minus 2 times 5 is minus 10, and minus 10 times 4 is minus 40. So this expression equals to minus 40 times cosine alpha. So we have two different equations for BD square. Therefore, we can do the equation 3 that says that BD square according to equation 1 must be equal to BD square according to equation 2. BD square according to equation 1 equals to 45 plus 36 times cosine alpha. It must be equal to BD square according to equation 2. BD square according to equation 2 equals to 41 plus 40 times cosine alpha. So here subtract 41 from this equation. So here 41 gets cancelled, and here we have 45 plus 41 is 4, plus 36 cosine alpha equals to, so cancel 41, we left only with minus 40 times cosine alpha. So here we did 40 times cosine alpha to this equation 3. So here we left with nothing, because it is minus cosine alpha plus cosine alpha equals to 0. But on the other side of the equation, we have 4 plus 36 times cosine alpha equals to 0. So 40 times cosine alpha minus 40 times cosine alpha is 0. So if you found out that 4 plus 76 cosine alpha equals to 0. Here subtracted 4 from this equation, if I found out that 76 cosine alpha equals to 4. Again, here we had 40 times cosine alpha minus 40 times cosine alpha is 0. So we have to add 40 times cosine alpha to this equation. So 36 cosine alpha plus 40 cosine alpha, 36 cosine alpha plus 40 times cosine alpha is 76 cosine alpha. So in total, this side of the equation we have 4 plus 76 cosine alpha equals to 0. Here subtract 4 from this equation, if I found out that 76 cosine alpha equals to minus 4. So you divide this equation by 76, and find out that cosine alpha equals to 4 over 76. 4 over 76 is 0.02, 0.0526, or minus 0.0526. So total we found out that cosine alpha equals to minus 0.0526. And we would like to find out the value of alpha itself. In order to find out the value of angle alpha itself, we just have to operate the inverse function of cosine on the result of this equation. We get the value of alpha itself. So inverse cosine, if we operate on the result from 0.0526 is equal to alpha. So alpha equals to 93.017 degrees in size. And again, this is alpha, this equals to 93.017 degrees in size. So in the next step, we implement the law of size in this white triangle BDC. Okay, click on the law of size. This is triangle ABC that could be any triangle. Angle BAC equals to component A degrees in size. This is angle ACB that equals to component C degrees in size. And finally, this is angle ABC that equals to component B degrees in size. So according to, and we also know that triangle ABC is described by this angle with reduced R. So according to the law of size in this proportion, we get that A over sin C equals to B over sin B equals to C over sin C equals to 2R. And again, R is the radius of this angle that blocks triangle ABC. So we can implement the law of size in this triangle BDC. According to the law of size, we get that BD over sin alpha equals to 2R. According to the law of size, in this triangle BDC, the following equation is solved. BD over sin alpha equals to 2R. BD over sin alpha equals to 2R. So first of all, we have to find out the value of BD itself. According to equation 2, BD squared equals to 41 plus 40 times cosine alpha. So BD squared equals to 41 plus 40 times cosine alpha, and alpha is 93.107. So BD squared equals to 41, and the value of this expression, 40 times cosine 93.107 equals to 2.105. So total shareholder that BD squared equals to 41 plus 2.105, that is actually 43.105. Okay. BD squared equals to 43.105. So we took note of this equation. And the square root of 43.105 equals to 6.565 units in itself. And BD equals to 6.565 units in itself. So total, according to the law of size in this triangle ABC, the following this triangle BDC, the following equation is law. BD over sin alpha equals to 2R, and R is the radius of this circle. That is the law of size. BD over sin alpha equals to 2R. We just found out that BD equals to 6.565 over sin 93.107 equals to 2R. So total this expression equals to 6.5745 equals to 2R. Here we divided this equation by 2 and found out that R equals to 6.5745 over 2 is 3.287 units in itself. So the radius of this area equals to 3.287 units in itself. So finish working on the first question. The next step, I put it on the solution of the second question. In the second question, our task is to find out the area of this green shape. And again, in the second question, our task is to find out the area of this green shape. So in that moment, we have the big quadrilateral ABCD. We know that AP equals to PB. We also know that AD equals to 9 units in length, DC equals to 8 units in length, and BC equals to 7 units in length. So our task is to find out the area of this green shape. So AB is a side 9, so if we focus on the lower side of the side 9 AB at point P, and the sum of the areas must be equal to 180 degrees according to over 3. So 90 degrees plus this missing angle total must be equal to 180 degrees according to over 3. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, we join points A and Q together by side 9, and join also points Q and B together by side 9. By doing those two constructions, we get those two right angles. So in the next step, we prove that the green triangle BQC can go into this right triangle again PQA according to side against side wall. So why those two right triangles can go into each other? First of all, we know it is given us the question that AP equals to PB. In addition, those triangles are both right angles and therefore they're equal to each other. If only PQ is a common side that belongs to both triangles, so we can write down that PQ equals to itself is a common side that belongs to both triangles. So in total, we should know that those two right angles can go to each other according to side against side wall. And from the fact that those two right angles can go to each other, we know two things. We know that they have also the same area, so the area of this rectangle is A, then the area of this rectangle must also control can go into each other. And so the first thing that we concluded from the fact that those two rectangles can go into each other, we concluded that they must have also the same areas. That is to say, the area of triangle APQ must be equal to the area of triangle PBQ. And the second thing that we concluded from the fact that those two triangles can go into each other is that side AQ equals to side QB. Again, AQ equals to QB according to the rule that says that corresponding sides of the triangles are equal to each other. So those two triangles can go into each other, therefore the corresponding areas the corresponding sides must be also equal to each other and their lengths. That is to say, AQ equals to QB. And again, AQ equals to QB according to the rule dimension. The next step is square both sides of the same equation and find out that AQ square is AQ square, DB square equals to DB square. So here we have, in total, we found out that AQ square equals to BQ square. Here we have AQ according to the quadrilateral. AQ square equals to AD square plus DQ square. And again, according to the quadrilateral, AQ square equals to AD square plus DQ square. And so we can substitute AQ square plus by AD square plus QB square, and likewise we have DB square. DB BQ square. BQ is the opposite of this QBC. So bq square equals to bc square plus dq square. And again, bq square equals to bc square plus dc square, while aq square equals to ad square plus dq square. So now, according to the equation 2, we should find out that ad square plus dq square equals to bc square plus qc square. So we have ad square AD is 9, therefore ad square is 9 squared over 81 equals to dq square. dq is x, therefore dq square is x squared. So in this side of the equation we have 81 plus x squared equals to bc square plus qc square. bc is 7, therefore bc square is 7 squared, that is 49 plus qc square. qc is 8 minus x, therefore qc square equals to 8 minus x square. So we know that 81 plus x square equals to 49 plus 8 minus x square. So 81 plus x square equals to 49, and 8 minus x square equals to 8 square, that is 64, plus x square plus 2 times 8 x times 2 times 8 times x, that is minus 16x. So here we have x square on both sides of this equation, so x square gets cancelled, so we cancel x square on this side of the equation, left only 81, while on the other side of the equation we have 49 plus 64 is 113, minus x plus 64. So in order to show that 81 plus x square equals to 49 plus 64 plus x square plus 16x. So here we have x square on both sides of this equation, so x square gets cancelled, so we cancel x square on this side of the equation, we have to leave 81, while on the other side of the equation we have 49 plus 64 is 113, minus, so in total we show that 81 equals to 113, here we have minus 16x. Again, 81 equals to 113 or 16x. Here subtract 16x from this equation, so here 16x will get cancelled. We added actually to this equation 16x, so x squared plus x squared is 0, so we have only 113. Here we have 81 plus 16x is 16x. So we found that 16x equals to 81, 16x plus 81 equals to 113. So here, subtract 81 from this equation, so in this equation, we have to leave x squared equals to 113 minus so in order to find out that 16x plus 81 equals to 113. Here we subtracted 81 from this equation, so we will have to leave 16x, but in the other side of the equation we have 113 plus 81 is 32. So in total, according to equation 2, we should find out that 16x equals to 32. Here we divided this equation by 32, divided this equation by 16, so we found out that x equals to 32 over 16, that is 2. X equals to 2, therefore 8 minus x is 8 minus 2, that is 6. the sum of those two one-sided interrogators is 180 degrees, therefore those two one-sided interrogators must be located between parallels. That is 380 is parallel to BC, therefore quadrilateral ABCD is a trapezoid, because it has one pair of parallel sides. So, in order to find out the area of the green shape, calculated the area of trapezoid ABCD by using two different methods. So the area of trapezoid ABCD according to the first method of calculation equals to the sum of its two parallel bases, AD plus BC, times the DC over 2. And again, the area of trapezoid ABCD equal to the sum of two parallel bases, AD plus BC, divided by 2 times DC. And DC is equals to 8. So if you found out that the area of trapezoid ABCD equals to AD, that is 9, plus BC, that is 7, divided by 2 times the DC. So the area of trapezoid ABCD equals to 9 plus 7 times 8 over 2. 9 plus 7 is 16 and 8 over 2 is 4. So in total, we found out the area of trapezoid ABCD equals to 16 times 4, that is 64. So the area of trapezoid ABCD according to the first method of calculation equals to 64 squared inside. But the area of trapezoid ABCD must be equal to the sum of the areas of the four components that it consists of. This is the area of this component plus this component plus this component plus this component. In total, the sum of those four areas must be equal to the area of this big trapezoid ABCD. Again, according to the first method, the second method of calculation, the area of this trapezoid ABCD must be equal to the sum of the areas of those four components that it consists of. Okay, so we calculate the area of each component separately, and then we add the areas together. This will be the area of the big trapezoid ABCD according to the second method of calculation. According to the first method of calculation, we found out that the area of this trapezoid ABCD equals to 64 square units in size. And according to the second method of calculation, the area of this trapezoid ABCD must be equal to the sum of the areas of those four components that it consists of. 1, 2, 3, 4. So the area of this entire AD equals to the base 2, that is the height 9 over 2. So 9 times 2 over 2 is 9. So the area of this AD equals to 9 squares in size. Those two targets can go to each other, therefore they must also the same areas. So if the area of this trapezoid is A, then the area of this trapezoid must be also equal to A. Plus the area of the fourth component that trapezoid ABCD consists of. So it will be equal to the area of this triangle BDC equals to the base of this triangle times, this is 6 times the height, that is 7 over 2. So 6 times 7 is 42, and 42 over 2 is 21. So the area of this triangle QBC equals to 21 square meters inside. So the area of trapezoid ABCD according to the second method of calculation equals to 9 plus 8 plus 8 is 2a plus 21. So that the area of trapezoid ABCD equals to 30 plus 2a. According to the second method of calculation, the area of trapezoid ABCD equals to 30 plus 2a. So the next step, so if we have two different equations for the area of trapezoid ABCD. Therefore, we can do the question 3 that says that the area of subdivided ABCD according to the first method of calculation must be equal to the area of this subdivided ABCD according to the second method of calculation. We already found out that according to the first method of calculation, the area of subdivided ABCD equals to 16 square root in size, 64 square root in size, and it must be equal to the area of subdivided ABCD according to the second method of calculation, that is 30 plus 2a. Okay, so if subtract 30 from the equation, we found out that 64 minus 34 equals to 2a. Here we divided this equation by 2, we found out that the a equals to 17, a equals to 34 over 17, this is a equals to 2a. A 44 equals to 2a. You substitute 34 in the equation. From order 3, it's 34 equals to 2a. Here we divide this equation by 2, and find out that a equals to 34 over 2 is 17. So if we found out that here a is 17, here also a is 17. So in total, we found out that 64 equals to 30 plus 2a, so a equals to 17. A equals to 17, so a equals to 17, and also a equals to 17. Our task is to find out the area of this green shape. The area of the green shape equals to 21 plus 17. 21 plus 17 is 38 square roots in size. So if we found out that the area of this ABCD equals to 38 square roots in size. So finish to append on the first question. In the next step, append on the solution of the second question. Actually, we appended on the solution of the second question. In total, we found out that the area of this green shape is equal to 38 square meters in size, and the radius of the circle the radius of this circle equals to the radius of this circle equals to 3.287 units in its length. Okay, thank you very much.